All right, today's lesson will focus on the basics of structure, and we're going to begin with the structure of the atom. You'll be expected to be able to determine the electron configuration of an atom just from the periodic table. We're going to show you some tricks for doing that quickly and easily. And then in part two today, we're going to look at bonding and the first of the structures that really dictate the engineering properties of materials that we are going to be focusing on this semester. So we want to begin with a major theme. There are two universal kind of concepts that tie this class together. The first of those is that systems are always going to seek the lowest possible free energy state. We talked about that last week. And the second is that the properties of materials are dictated by structure. And there's various levels of structure that determine those properties. At the fundamental level that we're going to talk about today is the structure of the atom is going to drive atomic properties, some of which are of interest to engineers, particularly stability, which would be radioactivity. And so if you're a nuke engineer or something, you're going to care a great deal about that. But the primary structure we're going to be interested in is the valence structure. That is, what does the outside of the electron look like, the outside of the atom look like, and the electron configuration in the outer layers, because that's going to drive the type of bonds that can be formed by the atom. The bonding types then are going to give us all of the things we're interested in thermal expansion, which you've looked at in lab, electrical and magnetic properties, which are related to some of the same things, obviously, that drive thermal expansion. And then the type of bond and the bonding ability is going to dictate the arrangement of larger groups of atoms and the type of crystal structure that is formed, which is then going to drive all of the mechanical properties of the material that we're interested in. So structure determines properties. We're going to come back to this. And as we've emphasized already, the goal of the class is to give you a general framework that's universal, so that you don't have to have detailed information about a material to know a lot about it, just from some fundamental pieces of information. And this is one of your big tools. If you understand how the different structures in general affect specific properties, you can come to any material, and if you know that structure, you know a lot of things about that material. So this is a major priority for us. All right, so we begin atomic structure. You've done this in chemistry. Nucleus has protons and neutrons, and we're surrounded by a cloud of electrons. And in the ground state, your number of electrons will match the number of protons, and that will give you an atom that is net neutral. Now, in general, a lot of what we're interested in doesn't happen to base atoms. It happens to ions, or it's ions participating. And an ion is simply an atom that has either extra electrons or is missing electrons. So sodium here, and here's all the electrons around it. In general, an outer shell that only has one electron or has very few electrons isn't particularly stable. So sodium will give this electron away and become a sodium ion. And the important point is an ion has a charge, a net electrical charge, and that's going to affect its solubility, the types of bonds it forms, its corrosion, its participation in corrosion reactions, and so on. So we're going to care about that a great deal. Now, on the periodic table, there's a bunch of numbers. This is, again, a review from chemistry, but the atomic number is your number of protons. And in a ground state atom, that will also be the number of electrons of a neutral atom. Your symbol, and then the atomic weight, which is the mass of an atom in AMUs, but for engineers, we really don't care about AMUs. That's going to be the mass of 1 mole of atoms, Avogadro's number of atoms in grams, at least in our solar system. So we begin with the electrons and ask, where are they? And the concept here we want to get away from is thinking of electrons as little satellites orbiting around a planet. That would be the old Bohr model. And it's just not particularly helpful, because as we talk about bonding and we talk about secondary bonding, in particular interaction with solvents and polymers, we need to understand that the electrons are acting like hyperactive preschoolers on the playground, and they're all over the place. They may be inside a fence. There may be a volume where we know we can find them, but where they are in that volume we really don't know at any moment in time. And so what's going to happen is where they hang out is going to be influenced. So this is called the wave mechanical model. We recognize that the electrons behave with the properties of a wave, and they're found in a probability space or a volume. Now, the question would be then, well, where are electrons going to go? How do they find a home? And they all have to have a home, and they can't shack up. In a sense, they cannot share space with other electrons. They have to have their own little spaces, their separate addresses. And so these are the laws, not the way they're framed in your chemistry book, but the way you want to think about them, maybe easy to remember. They're going to look for the lowest energy state. That is, they want to be as close to the nucleus as possible because they're negatively charged and the nucleus is positively charged. So they're going to be as close as they can get. But they repel each other because they're all negatively charged. And so they can't all get close to the nucleus. So there's going to be some stacking, and people are going to be pushed farther away. They're going to occupy distinct bands. That is, they cannot exist at all possible energy levels. They have to fill certain energy levels. It's like there's only 3 quality levels of housing, and you only have 3 price ranges that you can occupy. There's a low, medium, and high, and you want something in between medium and high, you're out of luck. Similarly, electrons can only exist in particular energy bands, and there will be gaps between those energy bands, and that's going to be really important when you talk about electrical conductivity, semiconductors, and so on. But the point is, particular energy levels must be occupied. Electrons may move between those energy levels. You can always upgrade your apartment by moving to a more expensive one, but you have to move to the options that are available. And the other thing is, remember that we're talking about a spherical volume, and so as you get close to the nucleus, there's not a lot of room. So there aren't going to be very many electrons really close to the nucleus. And so when atoms start having a lot of electrons, those electrons are going to get far away from the nucleus and have to be far away. All right. So gets us then to, well, what do these apartments look like, or what do we call them? And they're called orbitals. And orbitals exist within these energy level bands. And so you've got deluxe apartments, but there are first floor apartments and second floor apartments and whatever. And so these are subdivisions within the energy levels. And these are basically defined as volumes where you're going to find the electrons. Where they are exactly, you don't necessarily know, but they're going to be in that volume most of the time. Because we have that volume problem, the cubic dependence on distance from the nucleus for the volume available, as you go out to high energy levels, you're going to have more room, and so you have more orbitals. And so we're going to find that the high energy levels that are a long way from the nucleus will have many more orbitals available because there's a lot more room for them. There's 4 kinds of orbitals. So there's efficiencies and garden apartments and whatever. So the first of these is the s orbital, and it's a spherical distribution. You have to know these shapes. I think it's hard to see how complicated electron probability distributions are. P orbitals, and there are 3 p orbitals. If you look, there's a single s orbital, and the first number here reflects the energy level, and the s tells you the type. So in the first energy shell, there's 1 s orbital. In the second energy shell, there's another s orbital, and they're spherical. The p orbital, the p type, has 3 varieties, the x, y, and z. And so this dumbbell has room for 2 electrons with opposite spins, and this one has 2, and this one has 2. And the d orbitals, there's 5 of those, and then the f orbitals, there's all of them. Here's your s's, p's, d's, and f's. And you notice there's a pattern. There's 1 s orbital, there's 3 p's, there's 5 d's, and there's 7 f's. So you can just remember that, and you'll know how many. You're going to need to remember this sequence, SPDF, because that's not on the periodic table usually. But if you remember this, and then remember that these go 1, 3, 5, 7, you'll be able to use the periodic table for our nice little trick. I'm going to show you in a little bit. Okay. The other thing to understand is that each p orbital, or each orbital here, will actually hold 2 electrons. One of them has what's called a positive spin, the other negative spin. It's not spin in the way we think of it, has to do with their polarization, and we're not going to go there. But the point is each orbital holds 2 electrons, and that's the way things work. Now, we already said the different shells have different energy levels, and within those shells, the orbitals also have different energy levels. And this is a very nice graphic that shows you the relative energy levels. So for the, say, hydrogen, which would be your simplest atom, has only 1 electron. That electron is in a 1 shell s orbital, and the energy is very negative, is the way this is usually discussed. An electron that's free has no energy, and so as an electron gets close to the nucleus, it actually has negative energy. And you see there's a very large gap in energy levels between the electrons that are around hydrogen and helium and those that are on the outside of lithium and beryllium. And as you go out, there's a smaller gap to the p, and then here's the beginning of your 3 shell, 3s, 3p,